Example 4.1.3. A 10 to 1 ideal transformer is connected to a load of 1 plus J 0.5 ohms. The primary side is connected to a voltage source Vs equals 2500 angle 0 through a line impedance of 0.25 plus J 2 ohms. The polarity markings are those shown in figure 4. Determine the voltage and currents across the primary and secondary coils. Also verify that the power in the primary and secondary coils are equal. So the givens for this, I'm going to go ahead and do that in a schematic format. We've got a transformer. The primary side of the transformer has a voltage source of 2500 angle 0. And there's a line impedance connecting this voltage source to the transformer of 0.25 plus J2. So I've got a resistor and then an inductor there, 0.25 J2, and that connects to the primary side of the transformer. So that looks like this. And then the secondary side of the transformer serves a load of 1 plus J 0.5. Nothing is said about any sort of interconnect, so we'll just assume that that's the total load on the secondary side of this transformer. 1 ohm J 0.5 ohms. This is an ideal transformer, and the polarity markings that I'm copying from figure 4 are as I've indicated there. So just do some labeling. This is an ideal transformer, so that's the primary side voltage. The current flowing into the positive terminal of that is going to be the primary current, and similarly on the secondary side, we've got the secondary voltage, which is at the output terminals of the transformer, and we've got what's called the secondary current I sub S there. So that's pretty much the givens there, represented in a circuit schematic, where this portion right here represents the transformer itself. So we are asked to determine the currents across and through the primary and secondary coils. So basically that's, or the currents and voltages across and through. So that's IP, IS, VP, and VS. And then we're also asked to verify that the power in the primary and secondary coils are equal. In an ideal transformer, S on the primary has to equal S on the secondary. So P on the primary equals P on the secondary, and Q on the primary equals Q on the secondary. So all those hold. So that's the problem statement right there. The solution method here is, the solution is to draw or to form a system of equations, one for the primary side and one for the secondary side here, and then solve those equations simultaneously, so we can have multiple variables, multiple equations. We can solve those. There's a third equation that we have to do to solve this one, and that is that we have to relate the quantities in the primary side of the circuit to the quantities in the secondary side of the circuit using the turns ratio. Oh, I just realized I did not write the turns ratio here. That's a 10 to 1 transformer, so the NP over NS is 10 to 1 there. So anyway, we need to write these equations. We'll solve a KVL here, and then we'll relate the two together via the turns ratio. So starting on the primary side, we can see that the primary current enters these two devices. So there's a voltage drop associated with these as compared to the source, and then there's a voltage drop across the primary coil of the transformer. So if I were writing the Kirchhoff's voltage law for this loop right here, I would say that 2500 at angle 0 minus IP times 0.25, that's the voltage drop across that resistor, minus IP times J2, the voltage drop across that inductor. And then I've got minus VP, since I've got a voltage drop again, there is equal to 0. So that's one equation. Now I want to repeat the KVL analysis for the secondary side. I see I've got a voltage rise associated with the, if I choose a loop reference direction of clockwise here, so I've got a voltage rise across the secondary, so Vs is positive. And then current enters these terminals here, so these are voltage drops. So that's minus the secondary current times 1 ohm minus the secondary current times J 0.5 ohms. And so voltages around a closed loop sum to 0 in both cases. So I'd probably rearrange those and write them 2500 is equal to 2500 at angle 0 is equal to IP times 0.25 plus J2 plus VP for the primary side, and then for the secondary side I would write that the secondary voltage is equal to the secondary current times 1 plus J 0.5 ohms. So now I've got those two KVLs that represent the primary and the secondary side. So the problem is that's two equations and 4 unknowns. I don't know IP, I don't know VP, I don't know VS, and I don't know IS. So now I need to involve this transformer and the turns ratio to relate the quantities on the primary and the secondary side. Those two relationships are that the ratio of turns on the primary to the ratio of turns on the secondary is equal to the voltage on the primary divided by the voltage on the secondary. So that is one of the relationships. The other is that the number of turns in the primary divided by the number of turns in the secondary is equal to the current on the secondary divided by the current on the primary. So notice that those are flipped there, IS over IP in that equation. So if I were to rewrite this, I would say VP is equal to 10 VS, and I would see that substituting 10 to 1 in here for NP over NS, and I would see that IS is equal to 10 IP in this one. So we see that since it's a 10 to 1, this is a step down transformer. We're referring specifically to the voltage. The voltage on the primary side is larger than the voltage on the secondary side. The inverse is true of the current. The current on the secondary side is larger than on the primary side. So now we've got 1, 2, 3, 4 equations and 4 unknowns. So we would need to substitute these values into these equations and keep solving. So what we can do here is we can say, if it'll let me scroll a little bit, there we go. So that should give me enough room. So I'm going to substitute these values into the Kirchhoff's voltage law equations previously developed, and that's going to be 2500 at an angle 0 is equal to IP times 0.25 plus J2 plus VP, but I'm going to get rid of VP by just saying that's equal to 10 VS. So now I've gotten rid of one variable. And then here I'm going to say VS, VS is equal to IS, but I can sub out 10 IP for IS times 1 plus J 0.5. So now I've got two equations and two unknowns, IP, VS, IP, and VS. So I need to solve for either IP or VS and substitute. So that if I combine those two, I get 2500 angle 0 is equal to IP times 0.25 plus J2 plus 10 times this whole equation right here, 10 IP 1 plus J 0.5. So I've just substituted this in for the VS right there. If I solve this, I find that the primary current is equal to 22.14 at an angle of negative 27.42 degrees amps. And so now I can just start plugging that back into all of these equations. If I do that, I find that the secondary current is just 10 times that. It's 221.4 at an angle of negative 27.42 degrees amps. And then Vp is equal to 2,475 at an angle of negative 0.85 degrees amps. And the secondary voltage is 247.5 at an angle of negative 0.85. So notice that the transformer had an effect on the magnitudes of the current and voltage in the primary and the secondary, but not the phases right there for this ideal transformer. So now we've solved all of our variables, the primary voltage, primary current, secondary voltage, secondary current there. And what we want to do now is just verify the principle of the conservation of energy in an ideal transformer, and that is SP is equal to IP. Sorry, SP is not equal to IP. Well, so SP is equal to SS, the primary apparent power is equal to the primary second power. So SP is equal to VP IP star, and SS is equal to VS IS star. Apparent power in the primary is equal to the primary voltage times the primary current complex conjugate. Similar in the secondary there. So we just plug these numbers in here. We get SP is equal to 2475 at an angle of negative 0.85. And then we multiply that by the inverse, or the complex conjugate of this, which is 22.14 at an angle of positive 27.42. We get 54.8 kVA at an angle of 26.57 degrees. And then for the secondary apparent power, we get 247.5 at an angle of negative 0.85 degrees. And I multiply that by the secondary current, 221.4 at an angle of plus 27.42, since I take the complex conjugate. And again, I get 54.8 kVA at an angle of negative, or at positive 26.57 degrees. That's a 5 there. So I've verified the conservation of power.